Okay, so this is the exam taken last year, 2023. Not sure if this was the main or the recit one, but they are similar. We can cover the other one next week. So these are actually the questions related to the power system representation per unit system, as well as the short circuit analysis. On the left side, I'm projecting the questions, and on the right side, I want to discuss the solutions on the marking scheme. The first question is, what is per unit system and what are the benefits of using per unit system? Here there is a description, but you had also this discussion in the lecture notes, and you can go and check those notes we had, and feel free to discuss these parts. I don't want to discuss these descriptive parts. We focus more on the quantitative and numerical questions. So let's go to the second one, part B. 450 MVA 30 kilovolt to 20 kilovolt transformer has leakage reactance of 12%. I hope it's legible enough. If you are too far, you can sit closer. The first one is calculate the actual reactance value in ohm with reference to the low voltage side. So when we say with reference to low voltage side or high tension side, that defines how we calculate the base impedance. Because to calculate the base impedance, we need to know the base power and the base voltage. Power is the same on the two sides of the transformer, but voltage is different, obviously. So this is on the low voltage side. So you see Z base on the low voltage side, V square over S. Voltage on the low voltage side is 20 kilovolts. So here you see 20,000 square, or 20 times 10 power 3 square, divided by S. S is 450 MVA. So 450 times 10 power 6. And you get 0.0440. Now, the Z low voltage, the actual impedance on the low voltage side, is multiplication of the per unit impedance by this base impedance. So 12% or 0.12 times 0.044, that gives you 0.0053 ohm. So this is the answer to section I. This is the actual or ohmic impedance at the low tension side. Second part, II, is what is the reactance value in ohm with reference to the high voltage side. Again, as I said, if you see this question, it's nothing but repetition of the same approach in different sections. So here, again, we need to calculate the base impedance, but remember, this time you should put 230 kilovolts instead of 20, because we are in the high tension side. So 230 times 10 to the power 3 square over S. 450 times 10 to the power 6. This is going to be 117.55 ohm. And then when you go to calculate the actual impedance, you multiply the per unit impedance by this base impedance. 0.12 or 12% of 117.55. That is 14.10 ohm. Section 3. Suppose the base is changed from that 450 MVA to 100 MVA. What is the per unit value in the new 100 MVA base? So here we need to use that formulation, which is for transformation from an old per unit system to a new one. The big formulation includes also the ratios of the voltages. But here, in this specific question, the voltages are assumed to be unchanged. So we only need the parts for the power ratios. New per unit equals old per unit times new base power divided by old base power. So 12% or 0.12 multiplied by 100 MVA, which is the new base power, over 450 MVA.
So the old per unit is the leakage?
The given one. Old, yes, the per unit impedance is the given, is the leakage one, yes. Yeah.
But would you likely get this question as well as an impedance diagram question, like in the same paper?
Yeah, usually you have one question from transformers or per unit system and the other one about fault. Because when you go to calculate the fault, you also calculate the reactance diagram. So that covers the topic we had on the power system representation. Power system representation and then fault analysis. But this question, is only focused on the calculating per unit quantities, you see. And the fact that per unit quantities remain the same on the two sides of the transformer.
Okay, so you calculate the per unit quantity in the impedance diagram, so you sort of do it again for this, doing it twice.
Yeah, it's the same, yeah. Because, short circuit analysis need per unit understanding. I mean, they are together, if that is the question. I mean, you should study per unit part topic firstly and then go for short circuit analysis. Yeah, it's like we are assessing your knowledge about the per unit system 2 times in 2 questions. But per unit is something that you need in any case because that eases the calculations. Even if you skip this one, in the short circuit analysis, for that reactance diagram, again, you need the per unit. But there, except the transmission line, you need just to transit from an old per unit system to a new one. But here is more focused on converting the ohmic impedances to the per unit. It's more on the definition of per unit, except this section 3. You see, section 3 is transformation. So this is transformation from an old per unit system to a new one. Then section 4 says calculate the actual new value in ohm of transformer reactance on 100 MVA base. Reference to high voltage side. So section 4 in this question is very similar to section 2. The difference here is in section 2 your base power was 450 and your per unit impedance was 12%, while here in section 4 the base power is 100 MVA and the per unit is 0.026. So you need to use these quantities, but the same approach. So we need to firstly calculate the base impedance, V square over S, high tension side, so 230 kilovolt square over the new base, 100 MVA. That gives us 529 ohm as the base impedance. Then the impedance on the high tension side is the new per unit, 0.026, times the new base impedance, 529. That is 14.106. And if you check this value with what you got in section 2, you see they're exactly the same. Because no matter what base you're considering for per unit calculations, the actual ohmic impedance of the transformer does not change.
So is that the same for every time this question comes up, like 2 and 4 to be the same answer?
Not necessarily. Maybe we say low tension side, then you compare section 1 with this one. Okay? But yeah, this is actually the pattern we usually have had. And the other thing that you see in this question are those 2 descriptive questions. So even if somebody is not so confident with calculating per unit or some mistakes they may have, at least they can answer these 2 parts. Because in total there are 10 marks for part A and part C.
That's quite cool. That is actually quite a good question, isn't it?
Yeah.
Yeah.
Where did the 0.26 come from?
We had an extensive discussion about this in your lecture notes. So if you check that, we called it fault calculation main slide. If you go there, there are discussions bullet-wise. But here I'm just putting this just to say, yeah, your justification should be focused on explaining the reducing of the complication in calculation and things.
There's 0.026 come from ZHV, but that just comes from III, doesn't it?
Ah, you're referring to this section 4? Yeah, this is 0.26 because here they say calculate the actual new value in O in the new system. So when they say in the new system, I need to use the new per unit. You cannot use 12% anymore here. That leakage 12% had been calculated by the manufacturer based on 450 MVA. They got that 12% because they used 450. But in section IV, we should focus on 100 MVA system. So we need to use that per unit value. Okay, this was question 1 or whichever on the per unit and power system representation. The second question is about short circuit calculation. So this single line diagram is given. The first question is obviously about drawing the impedance diagram or sometimes reactance diagram and expressing all impedances to a common base of 3 MVA in this case. 3 MVA is our common base power. In this part, we are also asked to reduce it as much as possible to a single impedance. So, let's see how we map it. So what you see on top is actually the neutral node or reference node. Then, as this is a portion of the distribution network, we need to model that coupling point, this bus 1 fault level with a reactance XS. So this is my XS. We'll see how we got this number, but firstly, let's see how this diagram is drawn. So this is my XS. Then we reach this B1. So B1 always starts here after the neutral node. So B1 is here, then B1 and B2 are connected through this transformer. And this is my transformer. B2 has 2 generators. Again, it doesn't matter if they are upside down or the other way. From one end, these generators should be connected to this B2, and from the other, they are connected to neutral node. So you see these 2 generators here. This 0.5 per unit, 0.5 per unit. These are the generators. We will see how we got these numbers. So we just focus on the diagram now. Then, after this bus 2, there are 2 transmission lines, parallel. So these are my transmission lines. And then we have this B3. Again, you see B3 has a generator. So one end of this generator is connected to this B3. And the other side is connected to the neutral node. So you can extend this bus as long as you need so that you could draw this generator to be connected to the neutral node on top. Or like some textbooks, you can simply put a symbol of ground here. But this may be visually better to analyze this circuit. This looks like a closed loop circuit. So this is G3. 0.25 per unit here is G3, generator 3. And finally, you have this transformer, which connects B3 to B4. And that is here, 0.876. This is the last transformer. And this is B4, where I have my fault. The fault is there. So let's see how we got these values. Common base is 3 MVA. So the first thing I need is this X per unit. You could either prove it like me, or you can quickly divide the common base power by this fault level. So common base power is 3 MVA. You divide 3 MVA by 250 MVA. That's it. Because this is the inverse of S. Common base is given 3 MVA. Yeah, it's 3 MVA. So 3 divided by 250. 3 divided by 250, that is 0.012 per unit. So this is my excess. Then transformer 1, this transformer, the leakage or the reactance is 0.15 and the power is 15, which is different from my common base power. Mine is 3. So obviously you need to transform from the old one to the new one. So 3 is the new, 15 is the old power, and 0.15 is the reactance of this transformer. Reactance multiplied by new power divided by old power. And we put it here. These two generators are equal in terms of capacity and reactance, so we only need to calculate for one of them. We see the base power is different from ours, it's 1.5. So X equals the given reactance, 0.25, multiplied by new base power, 3 MVA, over old or given base power, 1.5, for both of these generators. That is 0.5 per unit, and we put them here. Then there are two lines, and as I said, normally for the lines we get ohmic values. So we need to firstly calculate the base impedances, then divide these ohmic impedances by those base impedances to have the per unit impedances. So base, Z base in general equals V square over S. We need to pay attention what is the voltage level of these transmission lines. So these transmission lines are in the 11 kV level. So we need to use 11,000 as the base voltage here. So 11,000 square divided by 3 million volts ampere or 3 MVA, because this is base power. 40.33 ohm is the base impedance for those transmission lines, and now you can calculate the X per unit. I've already excluded R here, it's not important because we are going to just calculate the reactance diagram. So, but if you want to also include R, it's the same. You divide 1 O by this 40 O. 1 O divided by 40. For the X, that is 2 divided by 40, and you get 0.05 per unit for the transmission line. And you map it here. There are 2 transmission lines. This is generator 3. Generator 3, I see the base power of generator 3 is exactly our base power, 3 MVA. So we don't need to do anything. So X for G3 equals 0.25. That is the value given in this question. 0.25, 0.25. Transformer 2 is the last device here. The given reactance is 0.73. The new power is 3, and the given power is 2.5 MVA, and you get 0.876 per unit, and then you can map it here. So this is your final reactance diagram, including all quantities in per unit and in new base. So now you need to reduce this network. So reducing, I don't have actually the steps here, but basically you see these two are series, you add them, that is 0.042. These two are parallel. You can replace them by just one because they are equal, and that is 0.25, because that should be half of these two. So this part, what you have is 0.25 and 0.042 parallel. You calculate the parallel impedance. This part, again, these two are equal. You can replace them with a single impedance, and that is half of them. That is 0.025. 0.025. When you worked out this part, you need to add to this because they are connected in series. And all what you get here is parallel to this one. And after you've done this part, that is connected in series to this one. So finally you get 0.92 per unit. So as I said, the process to reach to this is important, but it's up to you how you want to calculate. Sometimes students prefer to work out on this diagram. Sometimes the students want to go step by step, so they redraw this diagram step by step and they reduce it. They go for several iterations. But that is not the focus of our learning outcome. Obviously, that is important just to get the final number, but that is based on your previous knowledge of parallel and series impedances. So this is for section A, I believe. Yes, section A. Section B is calculate the per unit fault current for a three-phase symmetrical fault at B4. So here basically. So what you need to do is you need to divide 1 per unit by this 0.92.
Just quickly on that section A, the transformer side of things, is that solely just used at the top there? As in
Transformer?
Transformer? So
which one?
Top right of the schematic, essentially. Yeah, there.
This is the excess,
Oh, okay.
the fault level, and this is the transformer.
Yeah, right. Okay.
Yeah. Yeah.
Yeah.
So always, when you see that coupling point on top, between that one and your neutral node, you need to include that excess.
Yeah. Right.
And then the network starts. Basically, this network starts from this one. This is B1.
Yeah.
This is B1.
So I thought there wasn't going to be symmetrical faults in the exam. That one says about symmetrical fault. Is that wrong?
Well, yeah, this is symmetrical fault, yes.
No, there is.
It's not going to be asymmetrical.
This is symmetrical fault.
Yeah.
I'm moving to that.
Today we had an example. One of the section was on about symmetrical fault, so I wanted to attract your attention for that part. Sections B and C were about asymmetrical fault. And the other thing you learned there was in case in a mesh network, this is a radial network because it's a distribution system, but in a mesh network where you see some loops, in case you see some delta connections, you can transform them to star connection and then use this combination of parallel series impedances. So let's go to section 3 now. Oh, sorry, the question here. Calculate the actual fault current and fault level for symmetrical fault at B4. So in the previous section, we had the per unit value, but here we go for the actual value. The actual fault current is IF equals, so let me start with the actual fault level. So actual fault level is actual fault power. It equals the base power times the per unit power. What is the per unit power? The per unit fault power. The per unit fault power, or SF per unit, is exactly IF per unit. This one. So IF per unit and SF per unit are the same if VF equals 1 per unit. And that is actually true in most of our cases, because by default we are saying VF, the fault voltage, equals 1 per unit. So in this case, IF and SF in per unit are the same. So I used exactly this 1.086 here and multiplied by 3 MVA, and I got 3.25 MVA as the actual fault level. So this is okay. Then the other thing we are required to calculate is actual fault current. Actual fault current, I know the per unit current, but I also need to know the base current. To calculate the base current, you need to divide S by root 3V, because by definition, 3-phase power equals root 3 VI, in case V and I are line values, not phase values. So IF equals, you see, S divided by root 3, and this is my voltage here.
So let's say 415.
Yeah, I'm using this S actually, but it's the same, because what you need to do here is actually you need to multiply 3, which is your S, by the per unit IF. So basically you need to do 3 times 1.086. So instead of typing 3 times 1.086, as we already calculated this one here, I put it here. Okay? So in general, you're going to calculate an actual quantity. Actual quantity equals per unit quantity multiplied by base quantity. What is per unit quantity here? 1.086. What is the base quantity? That is 3 million divided by root 3 times 415. Because that is your base current. Last section, section D. If the fault level on bus bar B4 is limited to 3.20 MVA, so this is the limitation or tolerance, explain if the generator G3 can be operated or not. Sometimes they say, yeah, it can or it cannot, and you need to prove. Sometimes it's like an open question for you to find. So they say, explain if the generator G3 can be operated or not. So we say generator 3 has been already included in our calculation. So we can look at the case with generator 3 and see what is the fault level, and the case without generator 3. So the case without G3 is, you go back to this original diagram here, and you just exclude this one. Just exclude this one and recalculate everything for this part. So that means you are excluding G3. Without G3, you get 0.936 per unit as total impedance between fault node and neutral node. And if you use that impedance to calculate fault, you get 1.068 per unit.
Where does that 0.06 come from?
0.936?
0.6. Add them together. 0.06. Yeah, there you go.
yeah, this is, yeah, you need to work out here. I don't have the steps.
Sorry. Right,
Yeah.
okay,
Yeah.
yeah, no, that's fine.
Yeah. Now I want to focus only on the explanation of this question, and
Yeah.
once I've finished, we can look at it together. Anyone is interested in the
No,
mathematical
I-
calculation?
I-
Yeah.
I-
Yeah. Okay. So this is basically, you need to exclude G3 and recalculate the total impedance, and this is hopefully correct, the total impedance, and then you put it in this formulation to get the new fault current, which is 1.068, and if you multiply this by the base power, you get the actual power for this scenario, that is 3.20 MVA. So without G3, that is 3.20, and if the limitation is 3.20, that is hardly, I mean, that is exactly the limitation. So that means you should exclude this G3. We can see the other one here, you see, 3.25. This 3.25 is for the complete case where you had G3 as well. Correct? Because you got this one when you included G3. When you included G3, the fault level was 3.25, even 26, which is greater than 3.20 MVA, the tolerance of this bus bar. So the answer to this question is, yeah, we just obtained the value for the case without G3, and we can say on the boundary, this is possible to exclude G3, it's within the range, but if we include G3, then it goes beyond the tolerance.
You could just answer.
Can be operated or cannot. It cannot.
You could just answer that question with 2C, though, right? Because we've already exceeded it. So you could just say.
No, section C was just to calculate that fault level. But when you get here, yes, you need to refer that one in
You've
your.
already exceeded the 3.2 MVA anyway. So you could just say it can't.
Yes, well, sometimes you need to see even if you remove that G3, if that is still in the range. So that may be even still high, and you say including or excluding, you can never have this limit at your bus bar.
And then you just times it by 3 because of the three phases.
No, this is your base power,
Yeah.
because this is per unit, and this is MVA. This is the actual value. Okay?